So I think we can start. So yesterday we started talking about second order reliability method, but definitely we did not finish it. But what we did discuss is the motivation, or rather the need for a second order reliability method, because the natural question is, if there is a form of first order reliability method, why do I need a second order reliability method? And that importance, that need we did discuss. So I hope that part is clear. And then we started with the mathematics, but we did not go anywhere actually. We just did 2 steps and then we stopped. So let us start from the mathematics part, right? So in second order reliability method, we use second order Taylor series expansion. That's why the name second order. That is kind of obvious, right? We use second order Taylor series. Okay, and then this is what we are doing. We are saying that by that logic, if I do a Taylor series expansion about the MPP, which is my most probable point or my design point, I will get something like G of Z star plus grad of Z G Z star transpose Z minus Z star plus half Z minus Z star transpose Hessian, and we already saw what it is. It is basically the second order derivatives, right? And this one, and this is my second order expression. So I should write here approximation and not equal to, right? This is approximation and not equal to, because I have truncated the higher order terms. And then what did we say? We said that let us assume that Z and Z star both are on the limit state, the curve. And if both are on the limit state, that will give me 0 approximately equal to 0 plus grad of Z G of Z star transpose Z minus Z star plus half Z minus Z star transpose H Z minus Z star. Then what did you do yesterday? What was the next step that we did? We said that we want to simplify it. So I will rotate the coordinate and rotate it such that my primary direction is now along the gradient direction, which is the unit normal alpha, right? So what we did was, so we rotate the coordinate, and we rotate the coordinate, which means it will give me Z tilde is equal to R. R is my rotational tensor multiplied by Z, and Z is my random variable in the original standard normal space that we had. So in that same space, I am just rotating it, and rotating it such that the first direction aligns with the unit normal vector along the gradient. So, and that is why I said that Z tilde will be equal to alpha, which is the unit normal vector. So that is the basis function, right? Or rather, I mean, I am writing here Z tilde, but it is actually the unit normal vectors in Z tilde. So that will be along alpha, and then the other thing I said was Q. And these are orthogonal, obviously, because these are unit vectors. What was the dimension of alpha? Can you remind me? Louder. Alpha. k cross 1. Because I have k vectors, like in 3D it will be 1 0 0 something like that. So in that case, right? What is the dimension of Q? K cross k minus 1. Why k minus 1? Because that minus 1 is already there in alpha. If I write alpha and Q together, I will get k cross k. Right? So this is what we defined, and these are my, I will repeat it here, unit normal vector or the basis functions or basis vectors. Okay, these are my unit normal vectors. And then I have this quantity z minus z star, right? Z minus z star, which is delta z basically, and I want to write it in the new coordinate, in the transformed coordinate. So we write delta z is equal to z minus z star in the transformed coordinate, and that will basically give me delta z is equal to s times alpha plus q times t. Okay, s times alpha. So s is the projection of that delta z vector onto the alpha, that coordinate axis, and then q is basically my, again, q and t. Q is my k minus 1 unit vectors, and t basically is having the projection onto those k minus 1 vectors. So I will have a k minus 1 vector there. So I will repeat it here. S is, remember, a scalar because it is a projection onto a single axis. Alpha, the dimension is k. Q, the dimension is k cross k minus 1, and t, the dimension is k minus 1. And now if you do the calculation, you will realize that it's consistent. Okay, it's consistent. And then I said that now I want to take everything into this coordinate. So how will my Taylor series look like on this coordinate? And for that there was one more thing I did, which was g of z star. This is equal to g of z star this multiplied by alpha. And how can I write it? Because the gradient vector is in the, or rather alpha is in the direction of the gradient vector. So that means everything is orthogonal, they will have no contribution. So every other component will be 0, as simple as that. It's like something sitting on the x axis. In that case, I only get a I cap, b and c are 0. Same thing, right? And now substituting these two, let's call it equation 2. So substituting 2 into Taylor series, what we get is as follow: 0 is equal to, or rather approximate, but I am writing equal to, g of z star, and this is a scalar, so transpose will not act on the scalar, it does not matter. But alpha is the unit normal vector, so that will become transpose multiplied by this quantity. So S alpha plus qt, and this is my first order term, right? The second order term accordingly will be half S alpha plus qt transpose H S alpha plus qt. And then what will the first term look like? If I do the calculation, I will get a alpha transpose alpha, that will be equal to 1. I will get a alpha transpose q, that will be 0, orthonormality. So I will have grad of z star magnitude of that multiplied by s, and this is where we stopped. This is exactly the point where we stopped last time, right? So this is equal to grad of g of z star multiplied by s plus half. And now let us do one thing. Let us open the bracket and do the calculation. So what will I get? What is the first term? I see a s alpha plus qt transpose h s alpha plus qt. So if I do the multiplication, first term will be a square, because s is a scalar, and then alpha transpose h alpha, s square alpha transpose h alpha. What will be the second term? No, t is not a scalar. Qt whole transpose, so that means t transpose q transpose. When you do transpose of two things, they change. So t transpose q transpose multiplied by h multiplied by s alpha. Second term and first term, 2ab term. So qt t transpose q transpose h s alpha, and this s is a scalar that I can bring to the front, right? It will not be 0, there is a h sitting in between. Okay, so someone said 0, so this will be equal to s I am writing at the beginning, that's a scalar, t transpose, sorry, t transpose, not h, t transpose q transpose h alpha, and there will be a 2 here, because if I do the other side, you will get another one more term, plus what is the last term? The last term t transpose q transpose h qt, right? T transpose q transpose h q t. This is what I will get, right? Clear? So let us stop here at this point and now go back to the limit state surface and try to understand if we can say something about this 4 or 3 terms that we have. The first order term is fine. The second order, I now have 3 terms. One term is having s square, the other one term is having s times t or st transpose, the third one is having t square or t transpose t. So can I say something about these 3 terms, about the order of this term? Let us see, okay, because it is quadratic in what, s or t? That's the question. If it is what is quadratic in s might not be quadratic in t. So that is what I am trying to look at. Okay. So going back to the geometry, obviously this can be very high dimensional, but I am not doing that, or rather I cannot do that. So I am showing in 2D, right? But this z can be k dimensional, right? The limit state function is something like this, right? What we are doing? We are doing a quadratic approximation. So that quadratic approximation is probably, I don't know, let's say something like this. Remember that This is a quadratic approximation. You know that, right? Clear? And now what we are doing, we are writing it in terms of the new coordinate system. And how does the new coordinate system look like? Alpha is probably in somewhere this direction, right? So it's the normal, and q is the tangential. And in high dimensional, q now it is tangential direction. In high dimensional, it will be a tangential plane, and on that plane there will be multiple things happening. Okay. So this is my q. Okay. And again, keep in mind, I am showing alpha and q, but in reality, alpha is the unit vector in that direction. So writing alpha is like writing I cap. Writing q is like writing j cap. The equation is not I equal to j square. What is the equation now? For this, can you tell me what is the equation? Along alpha, what is the axis? S, right? Along q, t, right? Now, if I just take 2D, forget about high dimension. In 2D, where my q is a one dimensional, right? In that case, what will be the equation? How is S and T? How are S and T related? Yeah, so 4a are constant. So S is proportional to T square because of the parabolic approximation. So because of the quadratic or parabolic approximation, from here we can say that S is proportional to T square. Correct? Parabola. Which means if T is very small, S will be even smaller, less than 1, small. So if T is very small, S will be smaller. So therefore, from here, S is having a computation order of T square, right? S square will have a computation order of T to the power 4, and S times T will have a computational order of T cube. Okay. Okay, if I was not taking it to be 2D in this case, then S would have been proportional to T transpose T. I mean, that you know. I mean, T square would have been T transpose T, right? So that means wherever there is S square, that is fourth order in T. Wherever there is S T transpose or S T, that is third order in T. But we are doing second order reliability analysis. So that means we are only going to retain up to second order in T. Clear what we are going to do? So in SORM, we retain up to order of T square. This implies 0 is now equal to, the first term remains as it is, G of Z star multiplied by S plus half. Now, the first term, what is the order of this? 4. So that means I am going to ignore it. The second term, what is the order? Cubic. I am going to ignore it. So what I will be left with? Only the last term. Okay. So half, let me write it in this color, T transpose Q transpose H Q T. Clear what happened here? We used the fact that we are doing a parabolic approximation. From there we related S and T, and then we decided that we are only going to retain until second order in T. Because we are only going to retain up to until second order in T, any term that is having S square will vanish, any term that is having ST will vanish. And now if you look into it carefully, you will realize that even the first order term is actually second order in T, because that is having a S there. So even the first term, which is was a linear term, is actually second order in T. So this is what we get, right? From here, what is S? Sorry. So from here, S is equal to minus 1 by 2 T transpose Q transpose H Q by the grad Z star multiplied by T, right? Simple thing. I've just taken the scalar and taken it to this other side, and because of that the minus sign is now appearing. So this term inside the bracket has a name. It is known as the, can anyone tell me what is this equal to? This is known as the curvature matrix. Curvature is actually a function of the Hessian. Hessian is not the curvature. This is the curvature matrix. Now you can also call it curvature tensor, but let me go by matrix for now. Okay. So it is my K, and K I am already using, remember that, for number of variables. So I am going to write it like this. Two line means matrix, right, in that sense. So this is the curvature matrix, right? So this is my curvature matrix. Okay, so what do I finally get? I finally get S is equal to minus half T transpose K T. Okay. Now this curvature matrix, will it be diagonal, will it be full, what will it be? It will not be diagonal, it will be full. You have to diagonalize it. H is sitting in between. Because of that H and you are dividing by it, it need not be diagonal. Okay. It is not guaranteed that it will be diagonal. So we have to take it to the, you are right. Okay. So what we will do is that this K can be a full matrix, right? And we hate full matrix because the computation is very expensive. If you want to invert that, that's cubic in the number of dimension, right? So we will always prefer to make the matrix as sparse as possible, and the best thing is to make it diagonal, because then 1 by 1 by 1 by 1 by, that's your inversion, if you need inversion, that is. Okay. So even multiplication, whatever you think about, full matrix is the worst thing you can have in linear algebra. All right. So what we are going to do is that we'll use what we always use, the eigenvalue decomposition, one of the most popular algorithm of the last century. Actually one of the top 10 algorithm, eigenvalue, Fourier series, then there are some more machine learning things. So they are among the top 10 of the last century. Okay. So we'll do eigenvalue decomposition. Okay, this will have two lines just to be. So using eigenvalue decomposition, I can write K as U transpose lambda U, and lambda will now look like diagonal kappa 2 kappa K. It's a diagonal matrix, that's the eigenvalue matrix, right? Now I will stop here once and I will let you think and tell me why in the world I am starting from kappa 2 and not kappa 1. Because I could have started from kappa 1, but I decided to start from kappa 2. Now you may think that k, the dimension is k minus 1 cross k minus 1, and that's correct. But even then I can start from 1 and go up to k minus 1. Why did I choose to start it from kappa 2 and not kappa 1? And even not kappa 3, for example, let's say. 1 is for correct. Because this is in t. Kappa is, or k is in terms of t. The first direction is alpha, and we have nothing about alpha. If alpha was there, I would have used that kappa. So this is about the second, third, fourth and kth dimension. So it is about all those unit normals that are on the tangential plane. And to be consistent, I decided, or everyone decides, to start from kappa 2. So that is the reason. Clear? Clear, right? Okay. So now substitute this thing into the S. What will you get? S will be equal to now minus half T transpose, and now instead of K I will write lambda u T. Right now, no. But the idea is very simple. If you don't, the question is why are we diagonalizing, right? Yes. If you will realize very soon, if we diagonalize and write in everything in terms of the diagonal terms, even if we don't invert it, I will only need to compute k terms, diagonals. But if I somehow keep the final formula in terms of a full matrix, I have to compute k into k plus 1 by 2 or whatever the number is, right? So or assuming symmetric. If it is not symmetric, then k square, right? So that is the reason. But we will not do that. When you do the algorithm will start with the diagonal term. Right now the derivation, you will do the derivation. You do it once. The algorithm will not do the derivation for you. The algorithm will start from everything is diagonal in that form, right? So that is the point. And you are right. We will not invert it. We will not invert it. You are right. Okay. And also, yeah. So we will not invert it. So half T transpose U transpose lambda U multiplied by T, right? So let us try to arrange it. Half, that is a minus sign, sorry. T transpose U transpose lambda ut, which is equal to minus half ut whole transpose lambda ut, right? Now what is ut? U is your eigen vector, and when you multiply by t, it kind of rotates t in the tangential plane. So it is like if you have three axes like this, what you are doing is that suppose this is your normal alpha, about alpha you are rotating this in the tangential plane, because these two are forming the tangential plane in this case. In your case it will be k minus 1 dimensional tangential plane, and there about alpha you can rotate it and that will still be a valid axis. So this is what it is doing. It is rotating it on the tangential plane so that you can find out the principal curvature. Similar to principal stresses, this kappa 1, kappa 2, this thing, or kappa 2, kappa 3, these are known as the principal curvatures. Okay, and you know that principal stress we compute by eigenvalue decomposition. So principal curvature also will compute by eigenvalue decomposition. That thing does not change. Even moment of inertia, right? Mass moment of inertia, APL 100, right? Okay, so this is how it looks. So finally, minus half, this I am going to call T tilde transpose lambda T tilde, and now lambda is your diagonal matrix, correct? So what will be this equal to? Minus half summation n is equal to 2 to capital K kappa n Tn tilde square, right? Same thing, whatever you would get whenever something is diagonal. Okay. So this is your final expression of S of the principal curvature, right? So what we got is S is equal to minus, there is a 1 by 2 I am missing, no, I have written it here, minus 1 by 2 sum small n is equal to 2 to capital K kappa n T n tilde square, and this is my final expression for S. Final expression for S. And what is interesting and what is important here is that this S is having information about the curvature now. Now remember where we started yesterday, form was not accurate because we were either overestimating or underestimating that area between the original curve that we saw, right? And then we saw that second order is much better, and second order was better because it was incorporating that curvature information, at least in pictorially or geometrically. So that means we concluded that in second order, in our probability of failure expression, somehow the curvature information should show up, right? We have not yet reached that point, but now we have reached the point which is kind of the middle point right now of the whole derivation, where we have a S. We have a S, and the S is having information about kappa, which is the principal curvature. But yet we have not found out probability of failure, we have not done anything as such as of now, right? So is it clear till now? So I was hoping I will finish this yesterday until this point and then start from here today. Okay, so clearly I overestimated myself by half an hour, 35 minutes. So this was, I was expecting that I will go until this point, but I knew that it will not be possible, because I told you that SORM in one lecture is not possible. So this is the time when I started SORM yesterday. So one lecture is done and I have done 50% of SORM. So it's not possible to derive the whole thing in one, right? Okay. And that's why, by the way, these derivations you will not find in book. First of all, in book they will just give you the formula. In SORM, derivation is not there in the book. I mean, Haldar and Madhavan talking about. In other books it might be there, I have not checked, but definitely in Haldar and Madhavan I did not find the derivation. Okay. Form is there. SORM, they just give the formula. Okay. Anyways, so we are at a point where we have S, the expression of S, and it is having information about the principal curvature. Now I never wrote principal curvature, so I should write it at least once. So these are the principal curvatures. Okay. Okay, so this is the final expression for S. But S we don't care about. S has information of kappa, very good. But what is S? Why do I care about S? I do not. In reliability I care about probability of failure or reliability index, mostly probability of failure. S is some intermediate variable that was basically the direction along alpha for delta Z. That's what S is, S alpha plus QT. So that S was what? Some direction along alpha for delta Z, delta Z. That's what it is, right? So now, let us keep it in mind that we have arrived at something like this. but we are going to use it much later. We'll use it, but at some other point. Okay. So now let us go back. We started with delta z is equal to z minus z star. This is where we started, right? And this was equal to what? S alpha plus q t. Correct? Now we talked from this expression. By the way, that S we derived from which expression? The above x. We derived from the Taylor series expansion. Assuming z and z star sits on the limit state surface. From there we derived that. But can we not find out S from this expression now directly without relying on Taylor series? Can you tell me what will be the S from this expression? And that expression should not have anything to do with alpha t, first of all. So can you give me an expression of S from this expression that will not involve alpha t? Because those are unit vectors. S is the magnitude. So I want the magnitude of S without involving the unit vectors. Repeat. Norm. Correct. And that will be equal to what? Then I will go to quadratic of z. And from there I will find 2z z star. Do you think that is feasible? See, what you are saying that I will take a square of both sides, right? And that will give me what? I mean, what is the, okay, right hand side I will get a square plus q square. What is the magnitude of z minus z star? Do you even know that? So let us do a simple trick. Let us multiply alpha transpose to the both sides. What will happen? Alpha transpose alpha is 1, alpha transpose t is 0. Simple. Linear algebra. Right? Multiplying with alpha transpose, we get alpha transpose z minus z star is equal to S. S, right? But remember, I said I don't want alpha. I told you that, right? So I have to do something about that. So can you tell me what is alpha transpose z? What is alpha transpose z? What is z, first of all? It's a vector. It's a generic vector. What is alpha transpose z or alpha dot z? 1. I'll give you one easier. Suppose I have a vector. You said something? Repeat. That's a different thing. Forget about z star. I'm asking what is alpha transpose z? It's very simple. Let us see. Yes. Correct. It's a projection onto alpha. And alpha is what? It's my transformed coordinate. So it's a projection onto the transformed coordinate. It's the first component of that vector. It's very simple. I have a vector a I cap plus b j cap plus c k cap. If I do a projection with I cap, what will I get? A. If I multiply it, do an inner product with j cap, I will get b. If I do an inner product with k cap, I will get c. So in the transformed local coordinate, I will get alpha, some projection onto that. Right? That's what we get when you do a unit vector. A I cap plus b j cap plus c k cap dot I cap. You will get A. That means what is A? A is the projection of that vector onto x axis. Right? So this implies alpha transpose z minus alpha transpose z star is equal to S, which implies this is projection of z onto alpha. Let us call it z alpha. Like projection of z onto x1, I will call it z1. So in that sense. So let's call it z alpha, and that's the name I am giving. I can also call it Z1, right? Ultimately at some point, but yeah. Right? What is alpha transpose Z star? This you should be able to tell. What is Z star is along alpha, by the way. Z star is what? Design point. So it is along that. What will it give? 1. Magnitude of the distance. And what is magnitude of Z star? Norm of Z star? Beta. That will be beta. Exactly. So minus beta is equal to S. Right? Now, what is the S that we derived previously? Let us substitute that. Yes. So this is equal to minus half summation n is equal to 2 to capital K kappa n. My kappa for me only it is looking like chi square. Okay, so kappa, that is okay. Kappa n T n square, right? Which finally gives you Z alpha, that was not known, by the way, remember that, is equal to, by the way, that alpha is in the suffix, I mean Z1, Z2 like that, or subscript. So therefore, Z alpha is equal to beta minus half summation n is equal to 2 to capital K kappa n T tilde square n. Is this clear? I'll stop here for 10 seconds. So please look into it carefully and let me know if that is clear or not. It is clear? Okay. I have 5 minutes. Obviously, it will not finish today as well. Okay, so we'll go back on Monday. But let us try to talk about one concept and then I'll stop. Okay, and next lecture I'll start from that concept only. What I'm going to. So whatever 5 minutes I discuss, I repeat it actually generally. So yeah. So let us go back into the geometric things. Okay, and try to define probability of failure. So I'll come back to this. This is my equation, what, 3 or something. But let us go back. So this is my failure surface. Okay, and I'll stick at this. I'll not draw the second order term, but I'll draw the first order for this. Okay, clear? Now this distance is my beta, assuming that point is my most probable point or design point, right? Now how do you define failure? G of z less than 0. That is how defined. Phi, me, all those things are side things. Main you define as whether my limit state some function is being violated or not. That's what failure is, whether the deflection is more than whatever the body can withstand. That's what failure is, right? So we have been defining failure in that term. Here, for SORM, we need to define this failure in some other term. Okay. Remember what we have done is as follows. right? This is my axis. Normal is alpha or S, tangential is Q or T, whatever you want to call it, right? Generally S and T is what you will call it. Alpha and Q are the unit normal in those, right? So now in this alpha direction, can you define a limit state function? A limit state function that will be function of something in this S or alpha direction. What is the failure zone? The upper one. Safe is the lower one. So this is failure. This is failure and this is safe. And I am intentionally writing it weight apart so that safe and failure holds for both kind of. I am not going into the conflicted area, the area of conflict, right, which will overestimate or underestimate. So I am writing it here, right. Correct. If alpha transpose Z is greater than beta, that means that point is in the failure domain, which means Z alpha greater than beta is the failure domain. So from here, in form, and whatever you defined is only hold for form right now. Okay, in form, alpha transpose Z equal to beta. This represents the limit state that you already know, right? That is the point on that will basically give you beta, Z star, which is on the limit state, so that is 0. So that's the point on that. And if you keep changing this Z, by the way, I have not written Z star, I have written Z. So that means it can be some other point. So it will be some point on the limit state surface, form surface, form. Every. So it will be something on that form surface, right? Now, as correctly pointed out, alpha transpose Z greater than beta. That means that point is on the other side of the curve. That's why when you are projecting, you are getting a value. That will be your failure. And obviously the other one you don't care about, but this is my safe domain. This was happening in case of form, right? What will happen to this in case of form? And keep in mind, alpha transpose Z is Z alpha. I will give you a very simple clue. Go to the expression at the top. What changes in case of how can I go from that expression to form? I'll not include the information about curvature. Correct? So then that expression itself should tell you that if Z alpha is equal to that term, that means Z alpha is on the limit state. If Z alpha is greater than that term, the top one, that is failure. If Z alpha is less than that term, that is safe. Clear? So similarly, in SORM, Z alpha being equal to what, beta minus, I think, yeah, beta minus half summation n is equal to 2 to capital K kappa n Tn tilde square. This is my limit state. I mean, this is denoting that that point is on the limit state. Z alpha greater than beta minus half summation n is equal to 2 to K kappa n Tn tilde square. This is my failure. And lastly, Z alpha less than beta minus half summation n equal to 2 to k kappa n Pn tilde square. This is my safe zone. Right? So that means not today. Today we are out of time. But in next lecture, what will I do after this? What do you think I will do? I will assume this at the failure as my limit state function and try to do some integration in the failure zone to find out some expression of probability of failure. So that is what we will do on Monday. Strong recommendation, go through this before coming on Monday. Because on Monday, obviously, I am not going to repeat all of this. It's not possible. You have realized that by now. So go through this before coming to the lecture. Obviously, or go through the video. I will upload it before that, because this is needed, you can understand. And we'll start from this, exactly this thing, we'll start from here. Okay, clear? So you will get an email from me today for the meeting regarding the project, which will be online tomorrow evening. Okay, thank you.